Looking at the night sky, it's easy to get the impression that stars burn eternally and quite uniformly. However, as we know, everything is not quite so. Stars form galaxies, galaxies merge with other galaxies, and they then create clusters. As for vast empty regions of intergalactic space, they don't last long, as the next new galaxy is not far away. Nevertheless, exceptions and nuances exist everywhere. Today, we will touch on the topic of interesting and unique locations of galaxies in the universe. But before we delve into the paradoxical nature of such objects in the universe, we need to reiterate and remind ourselves of two key basic concepts. Firstly, the speed of light is constant, and it's equal to this value. It's unchanging, never less or greater. Photons of light always move at the same speed, regardless of whether it's a solar flare, a black mirror, or a laser pointer. Due to this limitation in speed, it can't be greater or less, we, as observers on Earth, can see certain objects in the night sky with a certain delay. Perhaps this is where the famous saying came from: when we look at the stars, we are looking into the past. In practice, it goes something like this. If you look at the star Sirius, which is 8.6 light-years away from Earth, it means you are seeing photons of light that began their journey to you 8.6 years ago. If you look at Sirius today, you will see it as it was in the fall of 2014. And to see how it looks exactly today, you'll be able to observe it in July 2031. The same analogy applies to other objects in the universe. For instance, if we take a galaxy that is located 200,000 light-years away from Earth, it means we see it as it was when early humans roamed the Earth. Secondly, we need to understand what the photometric paradox is. Here's roughly what the night sky looks like near one of the world's observatories. The visibility there is astonishing, with stars visible that we couldn't even see with the naked eye in urban conditions. But here, we don't observe them. However, they are there. Their light just hasn't reached us yet. Even if we visually scan any point in the night sky, like this one, where we currently don't observe stars, and direct our thoughts billions of light-years away, we will still encounter a star in any case. Everywhere we look, we'll come across a star. And as we remember from the past, thanks to the rule of the speed of light, we can find new stars in the sky over time. Because their light hasn't reached us yet, the current night sky looks like this, but later it will look like this. And even later, it will look something like this. Unfortunately, such a sky will no longer be seen by anyone on Earth, as who knows how many years will pass. Perhaps there won't even be a sun. So, as you've understood, this paradox plays with the contradiction between the darkness of the night sky and the idea of an infinitely filled universe. Of course, the universe is not uniformly filled with stars, but due to our limited observation capabilities and the brief duration of our observations, even if we lived for 300 years, it would seem to us that everything is evenly distributed. We don't even take into account the fact that our Milky Way galaxy is tiny compared to the entire universe. In an ideal finite version of the universe, the night sky should be brilliantly lit with stars, and we should see something breathtakingly dazzling, unique, and brilliant in every direction we look, encountering at least one star. But one might think that if a star is extremely distant, its radiation intensity should significantly weaken, and we shouldn't be able to see it. However, the matter is that the brightness of starlight reaching us doesn't solely depend on the distance to the star, but also on the solid angle under which we observe the star. In general, the theme of this paradox is very interesting. So, if you want a separate video related to light, write it in the comments. So, finally, we can talk about our interesting galaxy. You can currently see its image and its brilliant name, MCG 0102015. It's located in the Pisces constellation at a distance of 293 million light-years from Earth. Around it, within a radius of 100 million light-years, there's absolutely nothing. Previously, this object was classified as an elliptical galaxy of class E, but images with higher resolution showed that it's a spiral galaxy with a bridge. Looking at this frame, one might falsely assume that it's surrounded by other neighboring galaxies. However, in reality, this cosmic trick, this galaxy, occupies a truly unique position. Out of all the entities known in cosmic space, it stands as the loneliest. The reason is that in cosmic space, an enormous number of galaxies are arrayed along cosmic filaments, thread-like formations that compose the large-scale structure of the universe. These galaxies are interlinked by gravitational forces, forming a grand structure. Amid these filaments are vast voids, spaces where there is very little matter, roughly 1 atom per cubic meter. Galaxies are extremely scarce within these voids. The MCG 010215 galaxy designates one of these voids as its home. This galaxy is so isolated from others that if Earth were situated within it rather than the Milky Way, we wouldn't have known about the existence of other galaxies until the dawn of the cosmic era and the construction of the first powerful telescopes capable of observing exceedingly distant objects in the universe. Until at least the middle of the 20th century, we would have thought the universe to be mundane and uniform, that is, if we ever made it there. Furthermore, its uniqueness lies in the fact that scientists previously found similar galaxies only in the Bootes constellation, where the colossal Bootes void is situated. Inside this void, around 12.5 empty troughs were discovered. These galaxies were given a special classification, void galaxies. These are objects that exist in cosmological voids, and they aren't numerous. The reason is that many of these void galaxies are connected to each other through void tendrils. These tendrils are often even straighter than their typical counterparts due to the absence of surrounding influences. These tendrils can be sufficiently rich to form impoverished groups of galaxies. According to one version, void galaxies themselves are regarded as pristine examples of galaxy evolution, having few neighbors and probably originating from low-frequency intergalactic gas. But as we know, the majority of galaxies in the universe are surrounded by numerous neighbors. For instance, the Milky Way is part of a gravitationally bound local group consisting of over 50 galaxies, and this group, in turn, is part of the vast Virgo cluster. Therefore, the most current conclusion at present is that this galaxy formed in a distinctive manner. Typically, star clusters emerge along filaments or thread-like structures from very hot and exceedingly sparse gas. However, MCG 010201 Pheem emerged not near any but within one of the giant voids between them. The authors of such research even presented their own scenario for its birth. Dark matter formed a vast, scattered halo of particles. Visible matter began to be drawn toward the center, colliding and merging with each other, resulting in the formation of a rotating disk. Inside this disk, stars gradually formed, arranging themselves into a spiral structure over time. Subsequently, dark matter began to heat up and change in density, while thin, thread-like structures connected to the galaxy's halo increased its mass. Visible matter went through a normal cycle of star activity. Our Milky Way and similar galaxies will eventually merge with their neighbors over billions of years. However, this galaxy seems to have a different fate awaiting it. On the contrary, it will move away from other galaxies, and new stars will continue to form within its spiral arms until the material necessary for their creation is exhausted. But this doesn't mean that its end is imminent. According to experts, it could exist for tens or even hundreds of billions of years. During this time, stars, remnants of planets, and even some black holes will vanish. However, the dispersed halo of dark matter persists much longer than any visible particle structure. Ultimately, it will break apart, expelling particles one by one. Yet, our understanding of dark matter is so limited that neither scientists nor contemporary science can even speculate about it. The essence of my video was to emphasize that we shouldn't draw conclusions solely from individual observations. Sometimes everything can change. In a different context, imagine if we were truly part of this galaxy. We would probably not even have seen this channel and strongly believed in its solitary nature, absent other formations in the universe. Absolutely all galaxies, except ours, are exceedingly distant astronomical objects. We will never truly know what transpires within these vast gravitationally bound systems. I won't have the fortune to visit there, and we cannot send an umbrella or any apparatus there. We won't learn if there's life or incredible forms of it. Unfortunately, the universe has taken away this opportunity because colossal distances separate us. Galaxies are scattered throughout the cosmos. Still, we must express gratitude as one of these galaxies once gifted us life, and now we observe them from time immemorial. we won't lose our desire to study them. However, to be honest, the nature of these objects eluded our understanding for a long time. Each galaxy now lives out its life cycle. They collide, merge with others, evolve in their own ways, die, and are reborn. Each one is unique and extraordinary in its own right. Practically everything you know about objects in the universe, planets, stars, moons, nebula, resides within galaxies. They've become a peculiar refuge for everything. Today, we'll discuss the types of galaxies that exist, their variations, and the secrets they conceal. To start, it's worth noting that the exact number of galaxies in the observable universe is still unknown, but with the naked eye, you can see 4 distinct galaxies in the sky. These are the Andromeda Galaxy, the Large and Small Magellanic Clouds, and the M33 Galaxy in the Triangulum constellation. However, despite the fact that we can perceive the outlines of galaxies in the sky or in photographs, galaxies do not have clear boundaries. It's not possible to precisely determine where a galaxy ends and intergalactic space begins. This is because the optical size of a galaxy can be different from the radius of the galaxy determined through radio observations of interstellar gas. Often, the term size of a galaxy refers to its photometric size, which is defined by a curve on the illuminated surface connecting points with the same brightness. The measured mass of a galaxy depends on its size, but for a clearer understanding, let's touch upon the main components that make up a galaxy's structure. Firstly, there's the nucleus. The nucleus is a small region at the center of a galaxy. When discussing galactic nuclei, most commonly, we refer to active galactic nuclei. These are nuclei where processes cannot be explained solely by the properties of concentrated stars within them. Active nuclei exhibit processes that release tremendous amounts of energy. Signs of active nuclei often include gas outbursts or high-power radio emissions. While not always the case, unusual behavior in active galactic nuclei is often attributed to supermassive black holes. This is currently the most widely accepted theory. Secondly, there's the galactic disk. This is a relatively thin layer where most of a galaxy's objects reside. The disk is a component of lens-shaped spiral galaxies. Within this plane, there are spiral arms where a higher concentration of young stars exists compared to the galactic center. Their motion is orderly, as they orbit the galaxy's center in nearly circular orbits lying in a single plane. The density within a galaxy's disk is relatively high compared to its surrounding components, such as the halo or the central bulge populated by older stars. Spiral arms, often observed in galactic disks, contain a higher density of interstellar gas and young stars. It is within one such spiral arm that we reside. Now, moving on to the term known as the halo. In astrophysics, the halo refers to the region surrounding a galaxy, which is invisible and hypothetical. The halo's outer part is of particular interest to researchers, as studying it can help determine where the gravitational influence of one galaxy ends and another begins. The galactic halo is an intriguing element in its own right, which I might delve into in separate content. Finally, there's a relatively rare component called a polar ring. For example, the galaxy NGC 4650 has such a component. In the classic case, a galaxy with a polar ring possesses 2 disks that rotate in perpendicular planes. The centers of these disks usually coincide. The reason behind the formation of polar rings is not fully understood. Galaxies with polar rings are a type in which an outer ring of gas and stars rotates around the poles. These polar rings, according to experts, are believed to form when 2 galaxies gravitationally interact with each other. The next galactic component is called the bulge. This is the central bright ellipsoidal component of spiral and lens-shaped galaxies. It primarily consists of old stars moving on elongated orbits. A typical population in the bulge includes red giants, red dwarfs, supernovae of 2 types, as well as variable stars like Cepheids or globular clusters. For instance, in typical lens-shaped galaxies, the bulge is larger relative to the galaxy's diameter compared to spiral galaxies. In my opinion, the bulge is one of the most interesting elements in a galaxy structure. There's also the pseudo-bulge, but we'll discuss that another time. Now let's talk about the bar, or colloquially the bar structure. It appears as a dense and elongated formation consisting of stars and interstellar gas. It acts as a main supplier of interstellar gas to the galaxy's center. Now that we know about these essential components, let's move on to galaxy classification and learn more about these stellar islands. In reality, there are different classifications of galaxies. For instance, the Hubble classification, or classifications based on infrared telescope data. However, we won't select a specific classification today. Instead, let's discuss the distinct types of galaxies. Let's start with elliptical galaxies. Approximately 25% of the galaxies we know are of this type. They have a high luminosity and resemble a giant, bright star, a luminous sphere shining brightly in the center and fading at the edges. Elliptical or spheroidal galaxies are mostly composed of old stars, giving them a yellow or reddish hue. New stars are scarcely formed within them due to the negligible amount of interstellar gas and dust. Although exceptions are sometimes encountered, elliptical stellar systems differ primarily in size and compression degree. They are classified by letters from E0 to E7, representing their degree of flattening. For instance, E0 corresponds to a spherical cluster, while E6 denotes a more flattened one. Additionally, in the classification, an E0 galaxy could be perfectly round or oval-shaped. In galaxies of this type, star formation has ceased billions of years ago due to the scarcity of cold gas and cosmic dust. Massive galaxies mostly contain extremely sparse hot gas, with temperatures exceeding 1,000,000 kelvins. However, in spiral galaxies, which we will discuss after elliptical ones, star formation processes continue almost uniformly. This is why the most massive stars in elliptical galaxies have already completed their existence, whereas in spirals, new stars are continually formed and observed. A prevalent example of an elliptical galaxy is M87. Spiral galaxies constitute the most common type and perhaps the most beautiful. They make up over half of all known galaxies. A spiral galaxy appears as a disk with a bright yellow sphere at the center, surrounded by winding arms of fainter branches. These arms can have a bluish tint due to the presence of special stars, white and blue supergiants. In contrast to elliptical systems, they exhibit several structural peculiarities. Firstly, spiral galaxies have arms where active star-forming processes occur. Secondly, they possess a stellar disk, a relatively thin layer of matter aligned along the galaxy's plane, where most of the system's objects and stars revolving around the disk's center are located. Thirdly, there's a notable presence of interstellar gas and dust, crucial for star birth. Many spiral galaxies have a unique feature called a bar, which extends from the center and is surrounded by spirals. These galaxies are classified with the letter S and vary in density and arrangement of arms. Generally, they have 2 or 3 arms, though in some cases, arms differ in size. All these arms, if not perturbed by galactic collisions, wind in the same direction around the center, where the main concentration of matter resides, including a supermassive black hole and a dense spherical cluster of old stars, the bulge. Our Milky Way galaxy and the Andromeda Nebula, which we will encounter in about 4 billion years, are both spiral galaxies. The Sun is situated between the arms, away from the galactic center. Its orbital velocity is approximately the same as the arm rotation speed. As a result, our solar system avoids hazardous regions of active star formation, often accompanied by supernovae. But it is worth noting that spiral galaxies are most often observed beyond the boundaries of galaxy clusters. Spiral galaxies differ in the degree of development of their spiral structure, which is noted in classification by adding the letter A to symbols. In galaxies with A, the main number of stars is concentrated in the central condensation, and the central arms are weakly pronounced or only faintly suggested. In SB galaxies, the arms are quite developed. In galaxies with SE, the main number of stars is found in highly developed and often scattered branches, while the central condensation has small dimensions. The most famous spiral galaxies are our Milky Way, the Andromeda Nebula, or, for example, the Galaxy of Waters. An intermediate type between spiral and elliptical galaxies is lenticular galaxies of type S0. Galaxies of this type have a bright central condensation strongly compressed and resembling a lens, while the arms are absent or very weakly traceable. Lenticular galaxies are primarily composed of old giant stars, so their color is mainly reddish. They differ from elliptical galaxies in that they have convexity and a thin disk, but differ from type A because they lack a spiral structure, In other words, the main population of such galaxies consists of old, large stars of red and yellow colors. 2/3 of lenticular galaxies, like elliptical ones, do not contain gas. In 1/3, the gas content is the same as in spiral galaxies, but star formation processes, though occurring, are very slow. A good example is the Spindle Galaxy in the constellation Draco. Even more interesting are the so-called irregular galaxies, neither elliptical nor spiral. Irregular galaxies do not possess any of the common forms. They are usually chaotically linked, with star clusters sometimes lacking a clear form or even a pronounced center. They are quite rare, making up about 5% of the total number of known galaxies. But why are they so different from their galactic counterparts? The reason is that it is very likely that each such star system was once elliptical or spiral, but collisions with other galaxies or close proximity to them distorted them. These galaxies are mainly divided into two types: those that have some semblance of structure, allowing them to be classified into some kind of galactic sequence, and those that do not even resemble any of the classes mentioned above. There is also a third type, the dwarf irregular galaxies, which have a low amount of heavy elements and a large amount of interstellar gas, making them similar to the galaxies of the early universe. Therefore, studying this type of irregular galaxies is of great importance for understanding the process of galactic evolution. But they also contain young, hot stars. Such galaxies contain a large amount of dust, which blocks a significant part of the light from the stars. I think that in such galaxies, there are planets where the sky looks as modest and dull as possible. Personally, I would not recommend observing them with a telescope. Bright examples of such galaxies are NGC 1427A and the Magellanic Clouds. Well, the galaxies that have certain features but do not allow them to be attributed to any of the classes mentioned above are called peculiar galaxies. The features of the structure of galaxies that are considered peculiar can vary. For example, a distorted structure due to interaction with a neighboring galaxy or the presence of dust lanes, ejections of matter, and so on. A classic example of a peculiar galaxy is the radio galaxy NGC 5128. In fact, today I have only talked about 1% of what I wanted to discuss with you. Today, we have only touched the surface of how these enormous star islands are organized, and in future videos, we will uncover the secrets of the most unusual, astonishing, and unique galaxies. If you ever find yourself in the southern hemisphere of Earth, you can observe the Magellanic Clouds in the night sky. Mariners of the southern hemisphere have been familiar with these two bright clouds resembling detached pieces of the Milky Way for a long time. They are the large and small Magellanic Clouds, separated by approximately 21 degrees or 42 full moon widths. However, in reality, this distance reaches 75,000 light-years. The Large Magellanic Cloud is located 160,000 light-years away from the Milky Way in the constellation of the Golden Fish. The Magellanic Clouds are the three closest galaxies to us. Our only neighboring galaxies are the Sagittarius Dwarf and the Great Dog. In reality, the Large Magellanic Cloud is the largest galaxy after the Milky Way and the Andromeda Galaxy. Astronomers classified the Large Magellanic Cloud as an irregular galaxy due to the prominent gas concentration in its center, but there is also a suggestion that it has a spiral shape and can gravitationally interact with the Milky Way. On the other hand, the Small Magellanic Cloud is located in the Tucana constellation at a distance of 200,000 light-years from Earth. It can be seen with the naked eye and appears as a hazy, diffuse spot. Astronomers now know that the Magellanic Clouds are dwarf galaxies that are satellites of the Milky Way. They are gravitationally connected to both our galaxy and each other, as they share a common hydrogen envelope. The Large Magellanic Cloud is 10 times smaller than the Milky Way and has 20 times fewer stars, approximately 30 billion. Its total mass is 300 times less than that of our galaxy. The Small Magellanic Cloud contains only about 1.5 billion stars. In the past, scientists believed that the Small Magellanic Cloud was a part of the Milky Way, but recent findings have shown that they are not gravitationally bound. They periodically pass by each other and then continue on their separate paths. The galaxy of the Magellanic Clouds is significantly different from our Milky Way. It is rich in gases, allowing for new star formation, and has a low abundance of metals, suggesting fewer generations of stars. The Large Magellanic Cloud moves in a circular orbit, experiencing strong gravitational interactions with our galaxy. The size of this star cluster is estimated to be 10,000 light-years, and in terms of the mass of celestial bodies and gas within it, it is 300 times smaller than the Milky Way. At the beginning of the study of the Magellanic Clouds, they were initially categorized as irregular galaxies due to their lack of a clearly defined structure. However, new observations revealed the presence of spiral arms and bridges. As a result, the Dwarf galaxy was reclassified into a specific subcategory, taking up a significant portion of the Golden Fish constellation. The Large Magellanic Cloud contains 30 billion stars, making it significantly larger and closer to Earth than the linked hydrogen stream and gas envelope. The study of the Large Magellanic Cloud has led to many important discoveries that cannot be underestimated. Unlike the stable age of our galaxy, dynamic processes accompany the birth of new stars. For the Milky Way, these processes ended billions of years ago. The Large Magellanic Cloud contains thousands of objects of the first type with a high metal content characteristic of young stars. But the most impressive object in the Large Magellanic Cloud is the Tarantula Nebula, an enormous emission nebula that is the largest known to astronomers. It received its name due to its appearance, resembling a tarantula spider. Within this gas cloud, which spans 1,000 light-years, new stars are born, emitting a tremendous amount of energy that illuminates the surrounding space. Catastrophic events, marking the end of a star's life cycle, are not rare in this nebula. In 1987, astronomers recorded such an event, which was the closest supernova to Earth. The central part of the Tarantula Nebula is known for its unique objects, including a massive star called R136A1. This star surpasses the Sun in weight by about 265 times and in brightness by approximately 10 million times. Its discovery led to the establishment of a separate class of luminous blue variable stars. Besides these blue giants, there is another significant star in the Large Magellanic Cloud, a red supergiant. Its temperature is relatively low, with a radius equal to about 1,500 times that of our Sun, and a brightness greater by 280,000 times. So, if you ever find yourself in the southern hemisphere, be sure to look up at the night sky and remember this video. Earth is one of billions of planets located in the Milky Way. Once upon a time, there was no sign of life on our Earth. However, thanks to thousands of factors and various random circumstances, life emerged on Earth. Over time, evolution did not stand still. It was a long process, but eventually, about 200,000 years ago, intelligent humans appeared. You too came into existence at some point, and when you were born, your existence was not even a concept. As you grew up, gradually aging, but sooner or later, we all face death. And any other galaxy is no different from the algorithm of human life. Galaxies too die, including our Milky Way. So let's explore what awaits the Milky Way in terms of its demise. Can the Milky Way end its existence before its natural lifespan? And more importantly, what factors can influence this? First, let's rule out the overused theme of colliding with the Andromeda Galaxy, starting with the fact that when the Milky Way was extremely young, it was overly active, much like a teenager aged 14 or 15, full of energy and ambition. The galaxy was birthing new stars at a significant rate, much more intensely than it does now. However, as galaxies age, their power diminishes, resulting in less frequent star formation. To determine a galaxy's age, you need to know its color. It's no secret that red galaxies are older, while blue and cyan ones are younger. But the paradox lies in the fact that while living on Earth with limited capabilities, it's not easy to determine the exact age of the Milky Way. This is where infrared light, which we cannot see but can detect with special equipment, comes into play. When it passes through gas or dust, it becomes perceptible. About 20 years ago, scientists believed that the Milky Way was a young galaxy. However, recent research conducted over the past decade has led to a grim conclusion. The intensity of star formation in the Milky Way is actively decreasing, but there are still significant gas reservoirs that could foster new star formation. These circumstances have left scientists puzzled about the true state of our galaxy. So, to understand the specifics of the Milky Way's death, scientists decided to first understand how a galaxy dies in general. To reach the end of its life cycle, a galaxy needs to rid itself of various cold gases that affect star formation intensely. This can happen for various reasons. Firstly, gas may escape the galaxy. Secondly, it may significantly warm up and cease being cold. Thirdly, it could theoretically be entirely used up. To make accurate assumptions about the Milky Way's current state, scientists find it easier to compare it to a neighboring galaxy, such as the Hot Dog Galaxy, known for its brightness, with over 300 trillion stars. However, the reason for this intense brightness might not be the stars themselves. In its center, there might be a very powerful quasar. Quasars are not objects, but events closely associated with black holes. The quasar is the source of light and heat, and it's quite possible that the quasar in the Hot Dog Galaxy is heating the gas responsible for star formation. Consequently, star formation in the Hot Dog Galaxy is practically non-existent. This leads to an interesting conclusion. Does the same situation occur in our Milky Way? A couple of years ago, scientists concluded that one reason for our galaxy's approaching death could be a supermassive black hole. This scenario is similar to that of the Hot Dog Galaxy. Currently, our Milky Way is surrounded by a massive outburst of gas. According to scientists' assumptions, this gas formed due to the actions of the Sagittarius A-star black hole, which attracted a huge amount of matter and heated up to the point of a colossal gas explosion about 6 million years ago. It was a galactic catastrophe. However, since Earth is located far from the center of the galaxy, this galactic hiccup didn't affect us. So the theory that a black hole is gradually causing the Milky Way's demise seems logical. It's a kind of galactic scenario. However, this theory has significant gaps and inconsistencies. The problem is that the black hole in Sagittarius A exploded too late. The black hole was active 6 million years ago, which is relatively recent in galactic terms, and it couldn't have affected star formation intensity. Therefore, besides the black hole, there must be another reason. Otherwise, we can make a rough conclusion that the black hole that could have hindered active and intense star formation in the Milky Way should have been active hundreds of millions of years ago. However, hundreds of millions of years ago, that very Sagittarius A black hole wasn't active. So assuming that the black hole Sagittarius A star is related to the future death of the Milky Way is foolish and unsubstantiated. So the cause of the Milky Way's slow demise might lie beyond the Milky Way itself. If we dissect the structure of our galaxy, it will be quite bizarre. The Milky Way consists of 3 main parts: a dense central core, spiral arms, and one of these arms houses our solar system. These spiral arms should be flat, not bent. As for the edge of the Milky Way, there you can observe a strange section of a deformed disk. However, the reason for their deformation is naturally unknown. But what's interesting is that in 2016, scientists discovered 3 very ordinary stars that didn't differ from thousands of other stars, except for one fact. They recently left the galaxy at speeds exceeding 600,000 kilometers per hour. This fact raised thoughts among scientists that the cause of the deformed Milky Way disk might be related to these 3 stars that left the galaxy. However, this notion can be easily refuted because the mass of the galaxy is too massive for 3 even large stars to deform the galactic disk. So the cause of the Milky Way's deformed disk might be in a dwarf galaxy. You see, our galaxy is enormous, yet there exist galaxies with only 100,000 or even 10,000 stars, and it's quite possible that such galaxies are the most numerous in the universe. However, they are very challenging to detect, especially near the Milky Way. Not because scientists typically observe large objects, but because the light from dwarf galaxies obscures the light from stars within our Milky Way. There is only one type of star that can help discover dwarf galaxies, and those are Cepheid stars. They change their brightness, making it easier to measure their distance than other stars. Therefore, if scientists find Cepheids in our galaxy, it means that they can easily detect a dwarf galaxy nearby. Consequently, beyond the Milky Way's edges, there might be a dwarf galaxy. Considering these 3 stars, Cepheids, they could help reveal their past and bright future. According to Harvard computer modeling, Based on the biographies of the discovered Cepheids, this dwarf galaxy pierced and deformed the Milky Way's plane millions of years ago. During this event, tens of millions of stars should have collided, at least according to scientists' beliefs. However, another scenario is possible because the distances in galaxies are colossal. Stars might not have encountered each other. But regardless, the Milky Way suffered a gigantic cosmic accident in any case. Furthermore, due to this collision, many stars came closer to each other, leading to gravitational interactions that significantly disrupted their movements and influenced their futures. For example, if you throw a stone into the water, you will see ripples spreading out in circles. The same effect could have been caused by the dwarf galaxy after passing through the Milky Way. These waves spread across tens of thousands of light years throughout the galaxy. However, one such collision wouldn't be sufficient to cause substantial damage to the entire Milky Way. But what if there were not just one dwarf galaxy? Surprisingly, scientists believe that dwarf galaxies often interact with large galaxies, and even now, the Milky Way interacts with several other dwarf galaxies. For instance, a dwarf galaxy from the Canis Major constellation is closer to us than we are to the Milky Way's core. So not all the stars we see in the sky belong to our galaxy. So what happens when numerous dwarf galaxies gravitationally interact with one large galaxy? We already know what one dwarf galaxy can do, but multiple dwarf galaxies could even alter the structure of large galaxies. If dwarf galaxies did not influence the Milky Way, it might not appear as we've observed it for thousands of years. Numerous interactions with dwarf galaxies could have reshaped the Milky Way. Moreover, gravitational interactions could have created an object in the center of the galaxy, posing a threat to the dwarf galaxies themselves. This galactic structure in the center of the Milky Way has an elongated shape resembling a bridge containing stars. However, this bridge might be harmful to the galaxy since it facilitates the suction of gas into its center. As you can well understand, the deficiency of this gas can disrupt new star formation. In the core itself, a supermassive black hole absorbs gas, and without sufficient matter, new stars cannot form. The fact is that due to the bridge and the black hole near the galaxy's core, there is no active star formation. But then, why aren't stars forming actively away from the center, for example, in the regular arms? The Milky Way galaxy has a diameter of about 100,000 light-years. However, it wasn't always this large. In its early days, stars formed. Moreover, as we know, our galaxy merged with other smaller galaxies, a process that continues to this day. When a small galaxy merges with a larger one, it gets fully absorbed by the larger galaxy. This means that the Milky Way doesn't necessarily have to collide with something to enrich itself with new gas. The most logical scenario is that the Milky Way is self-destructing. Let's look at other galaxies in the universe. However, with a slight detour. You see, the galaxies we see are billions of light years away. This means that we are looking into the past, seeing them as they were billions of years ago. By comparing them with galaxies closer to us, we can track their entire evolution, even the aging process. Based on this approach, astronomers analyzed around 300,000 galaxies and concluded that all dying galaxies, similar to the Milky Way, share a common trait: high mass. This means that galaxies have a mass limit. For example, spiral galaxies with a mass of around 1 trillion solar masses actively form new stars, while once they exceed this threshold, they begin to die. So the Milky Way has accumulated such a high mass throughout its history, mainly through interactions with dwarf galaxies. Therefore, it is gradually dying, or already dying. However, it's essential to note that there's still plenty of gas in the halo of the Milky Way. The galaxy simply refuses to form stars from it, which can be likened to cosmic overeating. To measure the weight of a galaxy, you only need to measure the speed of stars. The faster stars revolve around a galaxy, the heavier it is, thanks to gravity. Astronomical studies from Australian institutions determined the Milky Way's mass and concluded that it reached a critical point. Paradoxically, the galaxy's self-destructive gravity devours other dwarf galaxies. But can the Milky Way avoid its demise? After all, a collision with the Andromeda Galaxy is approaching. Besides, we've established that the Milky Way is killing itself with its own gravity. We'll continue discussing the future of our galaxy and what awaits the Milky Way when it collides with the Andromeda Galaxy. Will this event actually occur? In reality, the Milky Way and Andromeda are hurtling towards each other at a tremendous speed. But this collision is not as frightening as some specialists describe it. Let's start by saying that the collision of two galaxies will occur in about 4 billion years, and by then, new stars will have ceased to be born in them. They will be two enormous masses of gas that you won't distinguish from the night sky. But once the two galaxies collide, everything will change. When the Andromeda Galaxy approaches the Milky Way at a sufficient distance, the mutual attraction will stretch them into an elongated shape. Then, they'll pass through each other and eventually come together again, forming an entirely new galaxy. Gas clouds will start giving birth to stars again. After such a merger, the galaxies will experience a second birth, transforming two spiral galaxies into one elliptical galaxy. If people were able to witness such a spectacular display in the sky, nothing could be more beautiful. However, when gas clouds in the galaxy start giving birth to stars, they will emit a considerable amount of energy, setting off a chain reaction throughout the new galaxy. But don't celebrate just yet, as a new problem will soon arise. This cycle of new star production will be fascinating, but only for a while. This stage will lead the newly formed galaxy back to its destruction, because many of the newborn stars will become massive blue giants and supergiants. Then, they will start aging, and naturally they will die, and some will begin to explode with tremendous force, creating supernovae. These supernovae will actively eject gas from the galaxy, so the gas will quickly run out, and there won't be enough material to form new stars. This time, the galaxy will most likely truly die. For a newly formed elliptical galaxy to be completely deprived of the gas produced by stars, it will take hundreds of millions of years. However, even after this gas depletion, this new galaxy will face another devastating blow. Let's break down what will happen to the two supermassive black holes that were at the centers of the two galaxies that merged. Initially, they will revolve around each other, creating powerful turbulence. Eventually, they will naturally merge. Since the newly formed galaxy will have plenty of fresh gas, it will become a quasar. This quasar will heat up more and more, signaling the end of the star-forming phase, because the combined energy of the two black holes will create an incredibly powerful quasar, essentially being the last nail in the coffin of the newly formed galaxy. The quasar itself will generate intense radiation that will pierce through the gas. In other words, the new galaxy that had just been born will die again. In fact, galaxies with such a history, due to their size, constantly encounter various problems right from the beginning. The more scientists discover about galaxies, the more new details they find. In 2016, a class of galaxies was discovered that is nearly 10 times more massive than the Milky Way. Strangely, they somehow managed to form new stars. For example, the Digital Sky Telescope, over 9 years, studied a vast number of galaxies and discovered a new type called superspiral galaxies. These galaxies are several times larger and more massive than the Milky Way. Surprisingly, they indeed give birth to new stars, and as of 2018, approximately 50 such galaxies have been identified. This discovery suggests that in some rare and unique cases, very massive galaxies can indeed form new stars. So, could there be such a unique case for the galaxies like the Milky Way and Andromeda, which consist of two massive galaxies? If we consider computer modeling based on the collision of two galaxies, it shows that both galaxies strongly influence each other, and at the moment of collision, chaos ensues. However, over time, they can return to a spiral form. Therefore, superspiral galaxies likely formed in this way. Also, it's noteworthy that such galaxies have double nuclei instead of a single supermassive black hole, which suggests that they can survive galaxy collisions. Hence, it's possible that our Milky Way will become spiral again after colliding with the Andromeda Galaxy. But let's fast forward 6 billion years and try to imagine what will happen to the newly created spiral galaxy as it drifts through the cosmos. The spiral structure makes it even more stable, and the turbulence from the black holes in the center will no longer affect star formation actively, as the spiral arms have become even more substantial than before. So, in the distant future, the Milky Way will most likely become part of a new super-spiral galaxy. However, that's not the end of its story. The nearest galaxies to us, including Triangulum, Andromeda, and Dwarf galaxies gravitationally bound to them, will probably eventually merge into one massive galaxy. So, it's entirely possible that we will become part of one of the largest structures in the universe. Therefore, tonight, be sure to look up at the sky and come to a final conclusion. In space, nothing ever truly dies, it merely undergoes rebirth. 10 billion years ago, our galaxy was different, and in another 10 billion years, it will be entirely transformed. Space is something truly immortal, and in the cosmos, absolutely everything is possible. Often, the surrounding world appears ordinary and mundane to its inhabitants. However, once you take a closer look at it, everything turns out to be quite different. For a long time, we believed that our solar system was just one of many star systems in the Milky Way. It contains rocky planets as usual and gas giants as well. However, soon astronomy made significant progress in studying and modeling planetary orbits, and it turned out that our system is extraordinary, not merely because it houses Earth with intelligent beings. It all started with Jupiter. Its orbit deviates significantly from being circular. Its elongation, scientifically known as eccentricity, is 3 times greater than that of Earth. We know that it is challenging to alter the orbit of a celestial body, especially if it has a substantial mass. And the more massive it is, the harder it is to change its orbit. In the early days of the solar system, when young planets were forming from the protoplanetary disk, they had flat, circular orbits. To achieve their current elongation, there must have been some gravitational interaction with another object. Jupiter's mass exceeds that of Earth by 318 times, and all other planets in the solar system by 2.5 times. To stretch its orbit to such an extent, gravitational interactions of colossal scales are needed. But with whom? What planet could be massive enough to influence Jupiter? Uranus and Neptune are also peculiar. According to calculations, they should have taken longer to form in their current positions than the protoplanetary disk could have existed. The only reasonable explanation for this paradox is to assume that they first formed much closer to the Sun and then migrated farther away. But the main mystery in our system is Mars. Also, the rocky planets in general follow a pattern. The farther a planet is from the Sun, the more massive it is. This makes sense because the farther a certain part of the protoplanetary cloud is from the star, the less material from that part of the cloud will be expelled by the star's radiation and solar wind. At first glance, this pattern holds true. Mercury is 15 times lighter than Venus, and Venus is 1.18 times lighter than Earth. But then we have Mars. Here, the regularity breaks. It is 9 times lighter than our planet. Certainly, some issues can be resolved by suggesting that Jupiter's gravity pushed away from Mars some part of the planetesimals, the small bodies from which Earth-type planets were formed. However, calculations show that a planet comparable in size to Earth should have formed in Mars' place, and the issue is not with the calculations or the theory. Mars lies within the habitable zone of the solar system. If it had an atmosphere comparable to Earth's, it would retain enough warmth to have a climate similar to Earth's arid regions. But in practice, its atmosphere is 150 times thinner than ours, and its gravity is too weak to hold a denser envelope. This is a fact. Clearly, if Mars were 5 to 9 times more massive than it is now, it would be inhabitable. Observations of other planetary systems show that planets the size of Earth, Venus, Mars, and Mercury are a significant rarity. Rocky worlds usually have masses noticeably larger than Earth's, earning them the name super-Earths. So, are all the planets in our terrestrial group anomalies? Astronomers Michael Brown and Konstantin Batygin, supported by most global scientists, believe that a super-Earth exists in our solar system as well. However, it is incredibly distant from the Sun, hundreds of times farther from Earth, and tens of times farther from Neptune. In other systems, planetary migration, moving closer or farther from their stars, is, surprisingly, a common occurrence. A whole class of planets called hot Jupiters exists only due to their migrations toward their stars, but our Sun has none. Gas giants cannot form close to a star because radiation blows away light elements to more distant regions. However, after formation, a gas giant might lose orbital stability and collide with planetesimals that gradually slow down its rotation around the star. As the planet's rotational speed decreases, it carves out concentric circles around its star, while its gravity ejects objects encountered along the way from the system. As a result, hot Jupiters often leave their stars without terrestrial planets and get so close to them that they heat up to thousands of degrees. This scenario paints a clear picture. Our system might have been quite different at the beginning. The giant planets didn't necessarily originate where they are now. Astronomers have constructed several detailed mathematical models of the movement of bodies in the solar system and made an unexpected discovery. From the perspective of celestial mechanics, the original formation region of Jupiter, the one that would be compatible with its current eccentricity and orbital position, is located at a distance of only 3.5 astronomical units from the Sun, meaning 3.5 times farther than the current distance between Earth and the star. However, Jupiter is currently at an average distance of 5.2 astronomical units from the Sun, which is 250 million kilometers farther away. So, how did it end up there? Here, computer modeling came in handy. Collisions with planetesimals slowed down Jupiter's rotation around the Sun, causing the planet to move on its orbit more slowly and, consequently, start to approach the Sun. On its way inward, Jupiter's gravity caught up with Saturn. Terrestrial planets form more slowly than gas giants and complete their formation after them. Therefore, Earth and Mars were somewhat lucky. If they existed at that time, they would have been in danger. Jupiter stopped at a mere 1.5 astronomical units from the Sun, slightly closer than Mars. The formed planets would have received too strong a gravitational impulse from Jupiter, and their orbits would have been too unstable. There was a high chance they would be ejected from the system. Nevertheless, Jupiter's migration caused significant difficulties for the unborn rocky planets. Its gravity did its job. Gas and dust from this part of the protoplanetary disk were literally absorbed by Jupiter, and some of the planetesimals were thrown out of the system. The region where Mars formed was so depleted of material that it ended up significantly smaller than Earth. But then why did Jupiter not stay at 1.5 astronomical units from the Sun and instead turn back? The explanation is straightforward. Saturn, following Jupiter, eventually entered into an orbital resonance with it. This means that Saturn's period of 2 orbits around the Sun became equal to 3 rotations of Jupiter, a 3-4-2 resonance. The presence of orbital resonance means that the bodies regularly align with each other. The gravitational interaction between them sharply increases, and their orbits receive significant corrections. The interaction with Saturn pulled Jupiter back just in time. Imagine what would have happened if the largest gas giant didn't stop at 1.5 astronomical units, but reached 1 unit, that is, Earth's orbit. Perhaps there would be no one to ask questions in that case. Earth would have been a small planet like Mars, and fortunately, Jupiter's walk would not have left much material for its formation. If life existed on it, it would hardly be as developed as it is today. Some believe that Jupiter is Earth's protector, safeguarding the planet from asteroid impacts. Well, then Saturn becomes Earth's savior. Such a journey of Jupiter couldn't help but influence Uranus and Neptune. Initially, they were not farther than 17 astronomical units from the Sun. The migrations of Jupiter and Saturn eventually threw them onto more distant orbits. They remain there today. Uranus at an average distance of 19 astronomical units from the Sun, and Neptune at 30. But what about the presence of super-Earths in the solar system? This is the most massive class of planets, but there is not a single one in our system. They form faster than the smaller bodies of the terrestrial group, so by the beginning of Jupiter's migration, they could have already existed in our system. In this case, an unfortunate fate awaited them. They were destined to be destroyed by falling onto the Sun. The remaining material of the protoplanetary disk in the regions where rocky planets formed in the solar system was too little to form a second generation of super-Earths. All it managed to do was to form 4 planets, with Earth accounting for approximately half of the total mass. However, things are not as straightforward as they seem. Practically any computer modeling of early migrations in the solar system indicates that its current configuration is unlikely. According to the most plausible scenario, the planets should have been on different orbits with slightly different eccentricities. Astronomers pondered this problem for a long time until they tried introducing additional planets into the modeling. It turned out that with the presence of 5 giant planets in the early solar system, instead of 4 as it is today, the probability of the system forming in its current state increases significantly. Almost certainly, some 4.6 billion years ago, there were indeed 5 such planets, and the 5th one was an ice giant, similar to Uranus or Neptune. Moreover, astronomers Batygin and Brown, who proposed the hypothesis of the 9th planet orbiting hundreds of astronomical units from the Sun, note that it is most likely a large object, or one of them, that was once ejected by Jupiter's great journey there and back. So, practically the entire architecture of the solar system was determined by events that occurred before Earth even existed. In the place where Mercury, Venus, our planet, and Mars are now, there might have been super-Earths, possibly more than one. At that time, there were 5 giant planets, not 4. The chaotic migration of Jupiter and Saturn destroyed all ancient super-Earths, casting them into the Sun, and at the same time expelled the current 9th planet of the solar system. Jupiter and Saturn themselves moved away from the Sun, and Uranus and Neptune moved even farther. It turns out that the migration of giant planets is the key mechanism that governs the scenario of planetary system evolution. Those systems with hot Jupiters may be devoid of terrestrial planets and chances of habitability. Their giant planets are so hot because their migration ended close to the star. They did not have their own Saturn to reverse their orbits. The constant presence of giant planets on orbits close to the star makes the presence of smaller rocky planets within the habitable zone even less likely. However, there are systems where giant planet migrations did not occur at all. In such cases, super-Earths are formed on orbits close to the star. The most well-known system with such a setup is TRAPPIST-1, located 40 light-years away from Earth. It is still unknown how habitable they are, but if they are, there might be more than one habitable planet in such systems, sometimes even more than 2. Whether this is true or not, we may find out in the coming years, thanks to the James Webb Space Telescope, which will soon begin its work. Before the era of mass exoplanet discoveries, scientists widely believed that the solar system was a favorable place for the formation of Earth-like planets and life. However, today, knowing about the Great Migration of Jupiter, this hypothesis seems less plausible. Earth miraculously avoided destruction and was not ejected into interstellar space. It appears that the birth of a habitable home in our system was an extraordinarily challenging process, and the number of planets suitable for habitation here is noticeably lower than what one might expect in more stable systems. In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply. As each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned? The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, H.L. Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's Pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds, seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a fifth-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach. The correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and possibly life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration because carbon primarily emerges in stars that do not become supernovae themselves. However, carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, the time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing, the elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes Sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population-type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1 million kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1 million kilometers apart. Twin moons or planets orbiting a giant world or a binary planet could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri, captured using a powerful telescope. Globular clusters are massive collections of hundreds of thousands of stars forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, you could call this an incredibly close encounter of two civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every million years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today.